In the last class, we talked about how to calculate the voltage of a redox reaction, and I want to review that before we talk about the change in voltage when you change concentrations. So I want to look at these slides from last time. I gave you this chemical reaction where we had to find the two half reactions. And when you're balancing, if you want to try to find the voltage, you have to turn one of them around. You turn the one around that keeps everything on the same side. And when you multiply by a factor to equalize the electrons, you do not multiply the voltage. And then when you add the two half reactions, you can add the voltages and you get the voltage of the complete reaction. Since the E is positive, it's spontaneous. We also talked about Faraday's equation, where delta G equals the number of electrons you cross out when you're balancing times the constant times the voltage. Once you know the voltage, you can get both delta G and K. For the reaction we looked at, I plugged in 2 for the N, the voltage we got, and you get a negative delta G, and then you plug the negative delta G into the thermal equation, and you end up with a large K, and those three always have to go together. We kept looking last time that those correspond to the green row in this table. If you do one of those double line for the salt bridge type of notations, you write the two half reactions, turn the one on the left around, equalize the electrons, and add, and you get the voltage again. We then did another reaction where when you write the voltage, turn it around and multiply. We crossed out 10 electrons and the voltage came out negative or non-spontaneous. And when you plug in the 10 canceled out times the negative 0.15 volts, you get positive G. And when you use the G to calculate K, you get a very small k. And those three always go together. That is the red row in this table. The question I want to ask now, and make sure you understand this, is that just because all of the functions that are the final answer came out to be spontaneous, can you just from that alone predict what the signs of H and S will be? And the answer is absolutely not, because H and S are only tendencies. You have to take both of them into account in order to be sure of whether the reaction is spontaneous. In other words, even for the reaction that we were talking about, which has plus G, which means non-spontaneous, you cannot predict absolutely from that delta G or that delta H will be positive or that delta S will be negative. It's very easy to just look at the table and say, oh, positive G has to be positive H. But that shows a misunderstanding of what it means. See, H and S are only tell you whether the reaction is spontaneous in combination. And so just because you have a positive H doesn't mean the reaction will be non-spontaneous. And there's no way to tell from H or S alone. So a non-spontaneous reaction can still have a negative H if the S is able to make it non-spontaneous. The next thing we want to look at is if the standard E that you calculate is not what you want, is there a way to change it? And the answer is yes. You can change it, but primarily by changing the concentrations. We're not going to change the temperature because, as we said, 298 K is standard and electrochemical cells don't work well above or below that. But you can change the concentration in order to change the voltage. This is an equation called the Nernst equation, which is named after a man. And I want to show you first where that equation comes from, because the Nernst equation is particularly important for two reasons. First of all, it explains how batteries die, and it also tells you how can you adjust the voltage of a battery that's not quite right so that it's what you want. Since the Nernst equation deals with changing concentrations, we're going to start with the delta G equation that calculates delta G with changing concentrations. I'm then going to plug in minus NFE for the delta G's in that equation. When you do that, you can get rid of the NF by dividing both sides by negative NF. I did that here, and when you divide, you cancel the minus NFs so that the E is now the variable by itself. And this gets an equation where E under non-standard conditions equals the E standard minus that term. The thing about it is 3 of those numbers, R, T, and F, are all constants. And so if you plug in the values of those constants, you end up with the only variable being N, or the number of electrons you cancel out. Now, for some reason, they don't leave this equation usually in natural log. They convert it to base 10 log, and the only thing is that differs by that factor 2.03 whatever. If you convert the log to a base 10 log, this equation at the bottom of the page here is the final form of the Nernst equation, and on exams I of course give this equation also, so nobody has to remember that number 0.0591. The V stands for volts, that's all it is. And I want to do a problem with this. This problem gives you a redox reaction, which I want to ask you first to get the E cell, and then what is the E without a circle when you change the concentrations of the ions. The two half reactions are in the redox table for acidic on page 11. You have to turn around the nickel equation to get everything on the right side. When you turn around the equation and add, you get the overall voltage, which is spontaneous. Now we want to use the Nernst equation to calculate the new voltage when you change the lead and nickel 2+ concentrations. You don't have to worry about changing the concentrations of the solids because they don't go in the Q expression anyway. So first you calculate Q, which is products over reactants, nickel ion over lead ion, which is 25,000. And then you plug in the Nernst equation, the voltage we calculated, 2 electrons are crossed out, and 25,000 for the Q. When you do that on your calculator, the voltage is now negative, which means it changed from spontaneous to non-spontaneous. This slide shows that since you removed almost all of the lead on the left, the lead ion, you would expect the reaction would proceed to the left, and it did. In the second part B, I just used different concentrations of the two ions. When I plugged in those two numbers, I ended up with a more positive E, which means there's an even greater tendency to be spontaneous. And you can see that from this slide because this time I removed almost everything from the right of the equation, so you should shift towards the right. Now this problem is an electrochemistry problem where I show you every one of the calculations that I want you to be able to do with the electrochemistry numbers. So I gave you a reaction there that has only two ions in it, MnO4 minus and 2 OH minus. The water's a liquid and the others are solids, so the only concentrations we have to worry about are the ions. And I want you to calculate E, delta G, and K first for that reaction. Then I want to calculate the new E when you change concentrations of the ions. The two half reactions are right next to each other in the basic table. I have to turn around the nickel equation, so I have to change the sign of that one. So it now becomes negative instead of positive for nickel. When you multiply the equations by 2 and 3 in order to equalize the electrons, they cancel, and so do some of the other things. So you get the reaction we started with, and the voltage is actually spontaneous because it's positive when you add the two voltages. Now, if you plug in the 0.098 volts and the electrons we crossed out, you get a negative delta G. And if you do it in the thermal equation, you get a large K. So here's that crazy table again. We're back in the top row, which is the go row. Now, in the second problem, part B, I'm saying what is the new voltage if you change the concentrations of the ions. And for this, you're going to have to use the Nernst equation, which means you have to get Q. So you're going to have OH squared on the top because that's the product, and MnO4 squared on the bottom. And don't cancel the squares. Some people do that, and it's wrong because x squared over y squared does not equal x over y. You can cross out the 2's if they're multiplied, but not if they're powers. So when I plug in the two numbers from the problem, I get 225 for the Q. Then when I plug in the Nernst equation, you put in the circle cell, 6 for the N and 225, and the voltage goes to a little bit down. And it doesn't really sound like that much when you go down, but pretend like instead of 0.098 volts, you are talking about a 9-volt battery, which wouldn't be, you multiply by 100, it wouldn't actually be 9.8 volts, but they do make it a little bit higher than 9 because they know that the voltage is going to go down as it gets used up. So if you start with a battery that starts at 9.8, by the time it gets down to 7.5 volts, that battery is dead because even though it's got some power left in it, it's not going to work the device that you put it in. And as soon as the voltage goes down below what the device needs, we call the battery dead and throw it out. So it's really the decrease in voltage that causes batteries to die. I want to talk about some real batteries, which I told you we were going to do in the previous lecture on electrochem. The main one that I'm going to use as my example is the car battery, which everybody's familiar with, but I want to show you a couple of others. The one I have listed as a hearing aid, alkaline battery, is also a watch battery, they call them. They're those little silver button batteries. And the half reactions that I'm showing you there are old ones. They don't use these anymore for the real ones. The thing is that all batteries have to be based on two half reactions because the half reactions need to be able to transfer electrons through a wire. That's how you make a battery. And you can add the voltages here to get the overall voltage. This is called an alkaline battery because it's under basic conditions, OH. You know, alkaline batteries are usually stronger than the other types, like Duracell and Eveready. And the thing is, it's just, they're called that because they're based on basic reactions, which is a synonym for alkaline. The kind of a battery that they use for the silver button batteries now is not that based on those two half reactions. It's actually based on what they call a zinc air cell. Now, if you look at that shape, the anode does have zinc in it, but the zinc is dissolved in liquid mercury, which is what's called an amalgam, and it's got potassium hydroxide. At the other side, at the bottom, the cathode, they drill a hole so that air from the atmosphere has access to the battery. So it's actually the O2 from the air that is actually the electron acceptor. And that's why they call it a zinc air cell. And you can see the kinds of things that they put in these batteries instead of a salt bridge. They have in this one a catalyst on a nickel screen. They have a separator between the two poles. These usually have little tiny holes in them in the membranes so that ions can move through the holes. And I showed you the half reactions down below. It actually involves forming a zinc complex, but the point is it's still the zinc that's losing the electrons, and this time it's the oxygen from the air that gains them. And of course, you never run out of oxygen in the air, and so this is how these batteries are made now. I thought it would be interesting to show you what's inside of a regular AAA battery. Somebody cut this in half, and what you can see inside is that there's a carbon rod that runs down the middle of the battery. That is, you can make carbon or graphite into a conductor in one direction if you make it into a pressed cylinder. And the coating of the battery is made out of zinc. And that's black stuff in the middle is a paste. And that's why they call it a dry cell, because it's not a liquid. It's a kind of a solid in there. And what happens is the zinc is actually the electron donor. So as the battery works, the zinc coating dissolves. And if you get a hole in the zinc coating, some of the stuff from the inside can leak out, and that is corrosion on a battery. But this is what they use for these kind, and I just thought you'd like to see the inside. Who's ever going to cut a battery open? So this is definitely following the same principles we're talking about. Now that battery that's a AAA is not rechargeable. If you try to reverse the electrons in that, you're not going to be able to get the zinc to recoat on the coating, because the zinc migrates out into the paste and it's lost. If you try to recharge a non-rechargeable battery, and there are people that do this every year, they try to put it in a battery charger, and a lot of people blow themselves up, because all you do is produce hydrogen gas that comes from the moisture in the battery, and hydrogen gas is flammable, so if you light a fire next to it, it can blow up the battery and part of the house. So they do, though, have batteries that are rechargeable. And the one I gave an example of here is a nickel-cadmium battery, which is an old type. They don't use it anymore because it lost charge just sitting on the shelf. But you can see the two half reactions very easily. And the thing about a rechargeable battery is they have to be made so that they minimize the entropy increase after each recharge. See, when a battery operates, every time a spontaneous process occurs, the entropy or disorder of the battery increases. That's what the second law of thermodynamics says. It's possible to make batteries so that you use internal features that keep it so that if you reverse the direction of the electrons and try to recharge it, you can actually somewhat regenerate what was at the two poles of the battery. And when you take the charger out, the battery will operate the way it did at the beginning, less efficiently, but it still works. The primary example of a rechargeable battery these days is a lithium battery. And I think the construction of these are fascinating. They have a membrane down the middle with little holes in it that lithium ions can move through and whatever other ions are there. So that's like the salt bridge. And they have found out that if you take sheets of graphite, which is just plain carbon, those are what they call fused benzene rings. You learn about this, aromatic rings. You learn about this in organic. But anyway, at the pole on the left there, the carbon sheets kind of make little shelves. And they found out that lithium metal the atoms sit right down on the shelves. So when this battery is operating, the electrons are going in the reverse direction from what they show you. The lithium ions in solution pick up electrons coming in, and they turn into the metal and they sit back down on the shelf. When you recharge it and turn the electrons in the reverse direction, you lose electron and the lithium comes off the shelf back into the solution. So when you run it again, it's got a place to go. The carbon shelves are what minimize the delta S because the lithium has a place to go back to, and there's a very minimal increase in delta S every time you use the cell. Problem with lithium batteries is that lithium is extremely reactive and it'll explode on contact with the air if you leave it out long enough. And about 3 out of 1 million lithium batteries actually undergo spontaneous combustion. And they figured that 3 out of 1 million is not bad. I don't know if you want 3 out of 1 million, because if your lap is the one that the laptop is sitting on when the battery all of a sudden starts on fire, I'm not sure you're going to be really happy about that. But lithium batteries are known to do that. I've seen pictures of it online. The guy is working with a computer at his desk. A fire all of a sudden starts and he runs away from the laptop while it's burning. It's kind of amazing. But anyway, lithium batteries are the ones that are usually used now in most of those portable rechargeable devices. Now I want to use a car battery as my main example of an electrochemical cell. So if you look, I put the two half reactions that a car battery is based on, and you can see that both of these half reactions involve lead. Why do they still use this? Because lead is toxic, and if you ever had a battery, you know that they ask you to bring it back to the company, back to where you bought it or where you bought the new one, and they will recycle it for you. Lead is toxic, and there's very corrosive sulfuric acid inside the battery. So the only reason they still use these is because nobody has ever been able to figure out a better battery to start a car. This was probably one of these were in the first cars that did not have to use a crank in front to crank up the ignition before you started it. You know, it's probably in the Model T, the non-cranking one. So anyway, they're still used. And I want to look at the two half reactions and see what you can tell from looking at them about how the battery's made. If you look at the half reactions, they add up to 2 volts. And the first question I ask you is, what are the substances that will be at the electrodes? You got to have something to wrap the wire around. Well, those are what the reactions start with. So there's going to be PbO2 at one pole and Pb solid at the other one. The problem with PbO2 is that it's a powder, not a metal, so they have to press it together into sheets so that it acts like a metal. So you can tell from the half reactions what the 2 poles will be. This is a cartoon picture of what a car battery looks like. I'm going to show you a more realistic diagram of one later, but there is lead and PbO2 inside, and the poles are attached to what the car uses voltage for. The next question is, what substance forms at each electrode? If you look at the half reactions, the substance that forms is PbSO4, and it's the same thing at both poles. I don't know of another battery that ends up having the exact same thing at both poles when it's dead, but this one is unique in that. The next question is, what's the electrolyte? Well, you know that when you make a battery, there has to be a solution with ions in it around the electrode. And if you look at the half reactions, the ions that are in both of them are H plus and sulfate. So the question is, what substance in water will give you H plus and sulfate ions? And the answer, of course, is sulfuric acid. This is one reason why they make so much of it, because this is the electrolyte in car batteries. And you don't even need a salt bridge, because H2SO4 is the same electrolyte at both poles. That's very helpful because you just fill the battery with sulfuric acid and it works. The problem is sulfuric acid is very corrosive. You know that if somebody gets sprayed with battery acid, they can get very bad burns and sometimes even are blinded by getting it in their eyes. Now this question is very important, and this is what you really want to understand. The question is, which way will the electrons flow in the cell? And you can tell this by which side the electrons are on in the half reactions when the battery is working spontaneously. Because of the fact that Pb solid has the electrons on the right, that means that is the electrode that they are being lost from. So that means the electrons are going to come out of the Pb solid, and the PbO2 is the one that has them on the left. So they're going to flow into the PbO2 electrode. So they're going to go from lead to PbO2. And here's the picture in the diagram. Now the thing about this is, car batteries are 12 volts, but the half reactions only add up to 2 volts. So how do they resolve that? What's interesting is that you learn in physics that if you hook up voltages in the way that's called wiring them in series, the voltages add. If you wire voltages in parallel, it's this reciprocal equation that is hard to predict till you plug in the voltages. But if you wire them in series, they add. So what they do in a car battery is inside they have 6 individual compartments. Each one of them are 2 volts, and they wire 6 compartments together in series, which gives you 12 volts. I couldn't find a really good picture of an actual car battery cut open, so I'm showing you by these diagrams. If you look, there's 6 compartments inside. Each one of them is called a wafer, and sulfuric acid is bathing the outside of them. If you look at the picture on the left, you can see that each one of the wafers has 2 PbO2 plates and 2 Pb plates, and the way they wire it is to wire them in series. And so the whole thing adds up to 6 volts, or 12 volts, I'm sorry. This is another battery where they take advantage of wiring cells in series. This is the inside of a 9-volt battery. Each one of those 6 batteries inside is 1.5 volts, which is what AA and AAA and D batteries and C batteries, they're all 1.5 volts. These are little ones, and there's 6 of them wired in series. If you take 6 1.5 volt batteries, it adds up to 9 volts. And that's the reason for the square shape in a 9 volt battery. Now I want to show you that if you have a car battery that discharges, you will get the same substance at both poles, PbSO4. Well, that's definitely dead. The thing is, you can get this to happen if, for example, you leave the door open and the dome light is on, or if you have an electrical problem that drains the battery. And so is there anything you can do about a dead battery? And you know there is. you can recharge these batteries using a battery charger. What a battery charger is it is a stronger battery that you put in the reverse direction so that it forces the electrons to go in the non-spontaneous direction. And usually battery chargers plug in the wall circuit from Commonwealth Edison, so you can make them very strong and force the electrons in reverse. They have portable ones, and I guess they do work, but the standard ones plug in the wall. When you make the electrons go in the reverse direction, this is what's called an electrolytic cell. And the word lytic refers to lysis. If there's nothing in the battery that can replate out on the metal at that electrode, all that happens is that you lyse water molecules into hydrogen and oxygen. And so these are called electrolytic. Unless there's something to plate out, then you won't split the water. So when you charge the battery, you really turn the two half reactions in this diagram around, and so the electrons go on the other side. At one pole, the PbSO4 turns back into lead solid, and at the other pole, it turns back into PbO2. And so you would expect that the battery would work again. And if you take the charger out, you would expect the electrons to go back in the correct direction. The problem with this is every time the battery goes dead, the entropy increases a lot. And so a battery might take 2 charges when it's gone completely dead. It may take a third, but more than likely it's not going to take more than 3 charges because of the entropy problem, so it's only partly rechargeable. You have a part in your car that recharges the battery continually as you drive. That part is the alternator. It takes the energy from the wheels rotating and uses it to recharge the battery slowly as you drive. And when you recharge it slowly, the entropy change is not as bad as when you use it up fast. And so it lasts longer and the battery stays charged as you drive. This is really the last problem that I want you to be able to do with electrochem. This to me is the main problem that shows that you understand the whole system. If you can just look at a picture like this and you can answer the question, which way will the electrons flow spontaneously and what voltage will you measure, and all you have to look at are redox tables. If you can do that, you really understand the subject, because this is how batteries actually work. So let's look at how you would do this. You first have to find a half reaction for each side of the battery. So you need one with iron and one with copper. The iron half reaction is at the top of page 12. And the copper half reaction is at the bottom of page 11. Now the next question is, which one do you turn around? The truth of it is that in a picture, the way I drew it, the electrons could actually go either direction. You can draw it either way. The question is, you want the electrons to go in the spontaneous direction. How do you make sure that they're going to be going spontaneously? The spontaneous sign for the voltage means that you have to get the E to be positive. So what you have to do is turn around whichever one of those two reactions will give you a positive voltage when you add the two together. If you turned around the iron half reaction, you're going to get negative 0.7, and when you add, it's going to give you a negative sum. So that won't work. The only reaction that you can turn around and get a positive result in the sum is copper. And so we're going to turn around the copper. If you turn around the copper, you make the sign of that reaction negative, and when you add, you get a positive voltage. And so you know that that's going to be the voltage that the potentiometer in the circuit shows. The question is, which way do the electrons go? In order to know that, you have to remember that the electrons on the right are being lost. And so since the copper is the one that has the electrons on the right, the copper is the electrode that's going to lose electrons, so the electrons are going to come out of the copper and into the lead. So the electrons are actually going from right to left. And if you put a potentiometer in the circuit, it doesn't change the direction. All it does is measure it. And so you're going to get a 0.434 voltage, and you're going to get the electrons moving from right to left. Now, since the beginning of the semester when we started studying redox, we now have 3 rules for which half reaction you turn around before you add. Number 1 is that if you're given a redox reaction, the something plus something equals something plus something, you're going to turn around whichever half reaction keeps everything on the same side I gave it. So, for example, in this reaction from last time, the MnO4 is on the wrong side in the half reaction from the table, so that's the one you have to turn around. The second one is that if you have one of those shorthands with a double line for the salt bridge, you always turn around the stuff on the left, which is usually the first half reaction you write. Here's one of those problems, and I turned around the cobalt because that is the stuff that's on the left of the double line. Today we have the third rule, that if you're given beakers that are drawn actually the way they look, the electrons could go either way. So if you're given a picture like this, the electrons could either go from left to right or right to left. The way you tell is that you turn around whichever equation makes the sum of the voltages come out positive, because that is the spontaneous voltage, and that's what we did in the problem today. Now I want to show you the law that applies to electrolytic cells, one of them, and remember that an electrolytic cell is produced when you force the electrons to go in the reverse direction from spontaneous. And in this diagram I called it an electron pump, which is really the same thing as a battery charger because you're pumping electrons in the non-spontaneous direction. They were going from copper to platinum spontaneously, but now you're going to pump them from platinum to copper in the other direction. What you really do by doing this is you turn the two half reactions around. And when you do that on the copper side, you're pumping electrons in, and so the copper ions in the solution pick up the electrons that are coming in, and they turn into the solid, and they stick to the bar, which is the process that's called plating out. So if you do pump electrons into copper, you're going to cause copper to plate out on the bar. Now the question is, how much copper is going to plate out? I mean, if you shut off the pump, you're not going to get any more plating. So it makes sense that the amount of copper that plates out is going to depend on how many electrons you pump through the circuit. This is another law that's attributed to Faraday. It's called Faraday's law of electrolysis, that the amount of metal you plate out depends on how many moles of electrons you pump into the electrode. The thing about this is that if you look at the charges of the metals that you sometimes plate out, Silver, if you want to plate that out, only requires 1 mole of electrons to get a mole of silver because the charge of silver is only +1. You only need 1 electron. Copper 2, if you plate it out, requires 2 electrons. And if you plate out a +3 ion, it actually requires 3 moles of electrons to plate out 1 mole of the metal. So this is the kind of a problem I ask you. It's always the same problem. It's just different metals and number of moles. I asked how many grams of copper will plate out from a copper 2 solution when you pump in 6.72 moles through the circuit. Now at this point, the American Chemical Society wants me to teach physics because they want you to calculate how many moles of electrons pass through the circuit by me telling you how long they leave the pump on at how many kilowatts. Now the problem with that is, first of all, I have to teach you about what's power or watts. In teaching that, you have to understand what coulombs are, because amps, which is the next step before watts, is coulombs per second. That's current. And you have to use that to somehow the number of coulombs to convert to moles of electrons. I don't want to teach physics. If you do physics 151 or 204, you're going to get all these electricity equations. I'm just going to tell you how many moles of electrons go through the circuit. So we're going to say 6.72 moles pass through. The first thing you got to realize is that in order to get 1 mole of copper, you have to get 2 moles of electrons because it's +2. The number of moles is determined by the charge of the ion. If you want to convert that to grams, you look up the weight in the periodic table. So that's how much copper weighs grams per mole, and that tells you how much copper you can plate out. Now, in order to see if you really understand this conversion, I want to ask you the next question. How would this problem change if you were plating gold out from a solution of Au3+? How would the conversion above change? We're going to start with the same 6.72 moles of electrons, but what's the next conversion? You're going to have to change the number of moles to 3 because the charge is +3. And of course, gold weighs a different amount than copper. And so, this is how much gold you can plate out. Now, I would just want to ask, do you think this might be an important calculation in the precious metals industry? Boy, is it. Let's say you were making gold-plated rings for a living, and you put a layer on a base metal of like 0.1 millimeter of gold. Well, it looks like a gold ring now because you can't see through the gold. If you put too much electrons in and you plated out 1 millimeter of gold, it's not going to be that much different. It's going to look like pretty much the same product, except you just used 10 times too much gold in order to make the same ring. So, of course, it's going to be very important to get just the right amount. And they also use this for purifying ore, for example, copper ore, and you have to do a lot of calculating for that also. So Faraday's constant, Faraday's law is important in industry. And the thing is, the amount that's plated out depends on how many moles of electrons you choose to pump in. Now here's that page with the summary of all the equations on it. These are the 5 equations that you would be given on the test if you were doing it in class. And these equations are all back on page 338 in the book. the delta G equation for changing temperature, the delta G equation for changing concentration, the equation where you interconvert G and K, the one where you can take the voltage of a redox reaction and calculate G, and also the Nernst equation where you can calculate voltages at different concentrations. So this is the end of the material that you need for exam 4. The next topic we're going to cover, nuclear chemistry, is lecture 15 and homework 15, and that will be on the final exam.